In this section, we're going to review how to find the determinant of a matrix. Now, we've already seen this a little bit before. We had to use the determinant to help us find the cross product of two vectors. So we're going to review the determinant in this section and go into a little bit more depth than we did when we just briefly introduced it when we talked about the cross product. Now, one thing that we didn't talk about when we crossed about the product is what good is a determinant? What does it tell us? What is it used for? So it turns out the determinant of a matrix is helpful for telling us whether or not the matrix is invertible. That's one of the uses of a determinant. But we're going to put off a more careful look at that until later. For now, let's just look at how we can find the determinant of a matrix. So we define the determinant of a matrix recursively. And it's going to be easiest to understand if we look at some concrete examples. All right. So let's start with a one-by-one matrix. So let's let matrix A be the one-by-one matrix with an element. Say it's equal to 5. Okay, so one row, one column, and the single element in the matrix is 5. Then the determinant of matrix A, we have a couple different notations for signifying the determinant. We could say det of matrix A, or if we wrap the matrix in between what look like absolute value symbols, that also means the determinant of the matrix. So two ways to express the same thing. Okay. The determinant of this one-by-one matrix is just the single element we plugged in. Okay. Notice, by the way, that this would be true even if this number were negative. We might don't think that these symbols that look like absolute value bars actually are absolute value bars. So for example, if I had a -5 here, the determinant of matrix A would still just be that single value, okay, for a one-by-one matrix. All right. Now let's look at 2-by-2. So let's let A be the matrix 1, 4, -2, 5. Okay. To calculate the determinant for a matrix of higher dimensions, we use the lower dimensions and then use a cofactor expansion. What do I mean? So we've seen this before. The determinant of this matrix A. So what we're going to do is we're going to expand along the first row. So I'm going to grab the first entry in the first row, imagine canceling out the row and column, and then multiply it by the determinant of what's left over. So in this case, that would be just a 5. So I have 1 times the determinant of matrix with just a 5. Okay, and then I go to the next element in the first row, 4. I imagine canceling out the row and column that the 4 is in, and then I multiply that 4 by the determinant of what's ever left over. In this case, that -2. So 4 times the determinant of -2. And then I just alternate sign. Plus, I don't need to write it because one's already positive, minus. Okay. Each one of these terms, which is equal to one of the, I guess I should actually include the sign there, which is equal to one of the entries in the first row times the determinant of what's left over after we cancel out the row and column that entry is in. That's called a cofactor. Hence why we call this a cofactor expansion, right? So notice, in order to get a 2-by-2 determinant, we need to know how to calculate a 1-by-1 determinant. And so we get 1 times 5 minus 4 times -2. That's going to be 5 plus 8, which is 13. Okay, now I'm being very careful here with these 2-by-2s. because we're going to have to use the same idea when we get to higher dimensions. But for a 2x2, it's usually actually easier to just kind of cross them. So 1 times 5 minus 4 times -2. Okay, so you don't have to think so carefully about these cofactor expansions. But when we go to a 3x3, that's when it gets a little bit trickier. And we have to be a little bit more careful. So let's let matrix A now be a 3x3 matrix. Okay, let's find the determinant of this 3x3 matrix. We're going to approach it much the same way. So the determinant of A, and again, I have two different notations. You only have to use one, but I want to be very clear that these are the same thing. Okay, and so I'm going to expand along the first row. Imagine canceling out the row and column. So I'm going to take that element 4 and I'm going to multiply it by the determinant of what's left over. 3, 0, -1, 1. So 4 times the determinant of 3, 0, -1, 1. Next element in the first row. Imagine canceling out the row and column. Multiply that 1 by the determinant of what's left over. 1, 0, 2, 1. And last element in the first row, cancel out the row and column. With that entry in it, multiply that entry by the determinant of the portion of the matrix that's left over. 1, 3, 2, -1. That's going to be 2 times the determinant of 1, 3, 2, -1. And then alternate signs. So plus, I don't really need it. It's already a positive, so I'll just leave it off. Minus, plus. Okay? All right, so that's the determinant. So each one of these is called a cofactor. You don't really have to, it's not super important that you know that. It's more important that you know the technique, but the technique is called cofactor expansion because we break it down into smaller cofactors. Okay, so we have these 2x2 matrices we want to take the determinant of. So I'm going to do it the quick way that I showed up here. Just take multiply the 2 along the main diagonal and then subtract the product of the 2 along the other diagonal. Okay, so 3 times 1 minus 0 times -1. And I'll write it out just since we're just starting off on this. Same thing here, 1 times 1 minus 0 times 2. Notice that order is important. First, you want to multiply the main diagonal and then subtract the product of the rest. Okay, if you get it the other direction, it won't be the same. Okay, you'll be off by a sign. So you want to make sure you do the main diagonal first and subtract the other diagonal. And then plus 2, 1 times -1 minus 3 times 2. And before long, you'll be able to do this very quickly. Okay, so we'll have 4 times 3 minus 1 times 1 plus 2 times -1 minus 6 is -7. So I have 12 minus 1 minus 14. And I get -3. That's the determinant of this 3x3 matrix. Now we could continue doing this. So 4x4, I'm not going to do it now, but later on I will show you. So 4x4, right? A, B, C, D. I won't draw all of it, but you would take the first element in the first row, then multiply it by the determinant of what's left over, right? After canceling out the row and column that element's in. Second element, you take that, you multiply it by the determinant of what's left over here. Notice at each stage what's left over is, in this case, is going to be a 3 by 3 determinant, right? If I cancel out a row and a column from a 4 by 4 matrix, I'm left with a 3 by 3. So I'd have to do 4 3 by 3 determinants in order to take a 4 by 4 determinant. Okay?